showing the overall structure of this course. So from week 1 to week 10, okay, from week 1 to week 10. So week 1 and week 2, so we'll introduce the hydraulic cycle. So what is hydraulic cycle? And also the impact, the urban impact on hydrology and the rainfall design. Means the urbanizations, the impact of urbanization on the hydrology and the rainfall design. Okay, so the major reason is the during the urbanization process, so the trees and also the vegetations removed and also replaced by the concrete or other impervious pavement or structures. Okay, so that will cause changes of the hydrology and also the rainfall runoff of the post-development area. Okay. Now, week 3 focus on the urban drainage systems. How to means design the urban drainage system. Okay. Week 4 to week 5 so covers the urban drainage systems and also the professional issues such as the water sensitive urban design. Okay, means to how to remove the pollutants. Okay, of the runoff. Okay, and also how to detention the runoffs. Okay, the rainfalls. How to detention the rainfall. Week 7 we focus on the stage discharge relations, and week 8 focus on the detention basin design. Okay, so the detention basin actually normally is used to reduce the peak run flow. Okay, to reduce the peak run flow and also to delay the peak flow time. Okay. So week 9, so we focus on the covers the water quality. Okay, and also the water sensitive urban design. So that means normally the runoffs from the catchment, especially those impervious catchment, include the different pollutants. They include different pollutants. So how to make sure the quality of water before releasing the water to the receiving body, such as rivers or the ocean. Okay, so. And last week's about the pollution reduction techniques and rain garden design. Means how to reduce the pollutant in the runoff and also how to design the rain garden. Okay, so the rain garden actually is a WSUD, means the water sensitive urban design. So it is used to remove the pollutant in the storm water. Okay, in the storm water. Okay. So this is the overview of the structure of this course. Okay, and I think now you already finished the week 9 lecture. Am I right? On tutorial. And for the storm water management, actually, for this course actually involves the design of drainage management and the maintenance. Okay, of drainage system for 2 purposes. The one purpose is to prevent the flooding if there's a rainstorm, and also to improve the water quality. Means to improve the water quality before discharging this water to the receiving bodies. So in this course, you can see that you will learn how to design a storm measurement system to remove the storm water effectively, and also at the same time to improve the water quality, to comply with the water quality standards. So according to overview of the course structure, so you can see actually this study we can we are focused on the 3 parts. Okay, 3 parts. Okay. So the first part, to design the conventional urban drainage system. So it means week 1 to week 5. Okay. So the to get the flow hydrograph at the downstream of the developed area. Okay, so that means how to design the urban drainage system. The first part. So the second part is to design a detention basin. Means the week 7, week 8 we'll focus on that. Sorry, no, week 6, week 7, and week 8. So design a detention basin and an outlet structure. Means how to bring the flood peak down. Means to lower down. Okay, to lower down the flood peak to the pre-developed stage. Okay, and the third part is about the water sensitive urban design. Okay, to introduce the innovative water quality improvement measures, WSUD, and to comply with the water quality standards. So before, I just mentioned that, before releasing the water from the detention basin to the receiving water bodies, such as rivers, streams, or oceans. Now, week 1, so we introduced the while we studied the stormwater measurement. Okay. So actually, this slide actually you can see that the stormwater actually management stormwater so could be hazard, threatening the life and property. Okay. So actually in Australia and also in Hong Kong, the extremes of the hydraulic variability so make the stormwater management a challenging for the engineers. Now, for example, in Hong Kong, I checked the I found the data from the website of DSD, Drainage Services Department of Hong Kong. So Hong Kong actually every year receives around 2,400 millimeters rainfall per year. Means 2,400 millimeters rainfall. Okay. And also about 80%, means 80% of the water falls in just a few months, means in the summer, June to September. Okay, in this a few months. So and also in summer, it's a high temperatures, hot and humid. So that's makes Hong Kong actually facing its flooding problem. Okay, flooding problem. So actually, here's the link about the let me see. I will introduce later. Actually, it's about the stormwater storage tank, underground stormwater storage tank, located in the Happy Valley. Okay, I will introduce that. Okay. So we can see uncontrolled stormwater runoff has many impacts. Has many impacts on the humans and the environment. For example, the flooding. So they could cause damage to the public and also to the private properties. So in cities, the surface runoff normally impervious surface, so cannot drain away quickly. Okay, so that means the runoff cannot be drained away very quickly, so which will result in flooding. Okay, because for the pre-developed area, means the pre-development area means with the trees, with the vegetations. Okay, so the surface runoff will be reduced because part of will stored, okay, in, for example, by the reception but interception of the trace of the vegetation or infiltration to the earth. So the urban area, so actually we can see that the most impervious, so the impervious surface runoff so cannot be drained away quickly, so which will result in flooding. And also the stormwater, uncontrolled stormwater also threatens the public health and public safety. For example, the pollutants of the drinking water, contamination of the drinking water, fish and shellfish, and also drownings occur in the flood waters. So I just mentioned that actually you can also see the in these slides conversion of an undeveloped area. So normally it's forested or pasture to a developed area. So increase the surface runoff quantity and increase the pollutants. Okay, increase the pollutants. And also another impact of uncontrolled stormwater is the increase the cost of the water and the wastewater treatment. Okay. For example, the pollution. Okay, so the pollution increases the raw water treatment cost and reduce the capabilities of the water bodies. And also the stormwater is also cause the flooding damages that is difficult and costly to clean up. So undeveloped areas, as I mentioned, normally they are pervious areas, such as the parks, lawns can soak up the most of the rain that falls there. Means the trees, the vegetations, and also the earth can soak up most of the rain that falls there. So only a small percentage of the rainfall turn to the surface runoff. Okay. So that's why the urban stormwater measurement systems becomes important. Okay. So the urban stormwater measurement systems certainly are designed to control the quantity. Okay, I mean there are two functions to control the quantity. Okay, to reduce the peak flow, and also to the second to improve the quality of the water. So you see that the urban stormwater management system are used to reduce the flood risk, reduces the flood risks, and also reduce the pollution of the streams and water or other water receiving water bodies. Okay, and also to maintain the ecosystem, functions. Actually, nowadays the climate change issues has becoming a worldwide urgent issues for all the countries on the earth. Okay, because the extreme weather becomes more and more common. Okay, and for example, this you can read the news about the heat waves in the North America. Okay, so and also improve the urban stormwater measurement system. Also improve the landscape and beauty of a town. So such as we can use the rain garden. Okay, to use the rain garden as the part of the urban stormwater management system. Okay. So you can see that the protect the urban waterways actually require integration approach. Okay, so we need to manage the volume, the rate, and the quality of the stormwater runoff. And also the habits, maintain the habits for supporting a healthy aquatic community. So actually, as I mentioned that the design criteria for quantity control, okay, the design criteria that there are two major design criteria. One is the quantity control, means the peak post-development runoff rate should be less than peak pre-development runoff. Means the peak runoff after the development, okay, should be less than the peak runoff of the pre-development period. And also the second criteria for the quality control, for the quality. So for the quality control, actually, you can see that. So we need to define level of treatment, okay, such as we use the detention basin, and also we need to have a specified detention time, okay, for the sedimentation, and also we also need a retention of a specified volume of initial runoff. So actually, the detention basins is used to remove the pollutants in the stormwater before releasing to the receiving body, before releasing to the receiving body. Actually, in recent years, the sponge city concept has been introduced. The sponge city. The sponge city means what that means. The sponge city. The sponge city means city could function like a sponge, has great resilience, resilience to the environmental changes and the natural disasters. Okay. Actually, now it has become more important for the cities to has resilience to the environmental changes, because the extreme weather now is becoming more common. Okay, so the resilience of the cities and also of the cities' infrastructures to the change, to the environment changes, becomes very important. So for the sponge city concept, okay, so the storm water could be absorbed, stored, infiltrated, and cleaned during the rainy days. Okay, so and then released and utilized to enhance the ecological function of the city and reduce the flooding in the city. So that means the sponge city actually, put it simple. So that means we want the sponge city has the function of the pre-developed, area. Okay, so that means they can absorb and store. Okay, absorb and store the storm water. Okay, and also clean the water and cleanse the water before releasing, and also can also utilize. Okay, utilize. So then a part of the stormwater can be utilized as needed, so to enhance or to maintain the ecosystem, to enhance or to maintain the ecosystem of the city. So actually, the sponge city actually is a modern stormwater management approach. So the cities can collect the rainwater and use stored rainwater when needed. Okay, so this concept actually will reduce the urban development through natural drainage of rain to avoid large-scale artificial channels. And also the as I mentioned, the storage of the stormwater. So the principle of the stormwater storage scheme actually is to temporarily store the stormwater during the heavy rainstorm in the underground, normally in the underground tank. Okay, so that can relieve the burden of the existing drainage system. Okay, so when the storm water in the downstream drainage system receded, so the storm water stored in the tank can be pumped out and relieve the storage space for the next rainstorm. So in Hong Kong, actually, I also get this information from the website. Hong Kong, actually, there are 3 underground stormwater storage tanks, okay, located at Tai Hong Tuen and Shan Wan and Happy Valley. I mean, 3 stormwater storage tanks. So just give examples of the Happy Valley underground stormwater storage tank. So actually, the Happy Valley underground stormwater storage tank actually is example of using the sponge city concept. So built under the Happy Valley recreation ground, the storage tank has a total capacity of 60,000 cubic meters for runoff storage during the heavy rainstorms. Okay. Here's a video of around 3 minutes 30 seconds. Okay, I think I can send you the link. Now here's a link. Okay, here's a link of this of the video showing the showing the Happy Valley underground stormwater storage tank.
Valley in Hong Kong is a low-lying area surrounded by hills
on so I'm not going to to share the video here. Okay, so you can click the link. Okay, and watch this short video during the recess or the break. Okay. Next slide is actually about the impact of urbanization on waterways. Actually, I just mentioned a little bit about that, the urban impact on the waterway, on how the urbanization impact the existing waterways, such as streams, rivers, or oceans. So the urbanization actually will change the hydrology of the post-development area. Will change the hydrology, such as erosion, change the current capacity, and change the groundwater recharge, and even change the stream morphology. So erosion. So because the exposed soils are easily to erosion, okay, because the vegetation is removed, and also you can see the this figure. Okay, this slide also showing a figure about role of vegetation in moderating the runoff. Okay, so you can see the importance of the vegetation. Means the importance of vegetation in the pre-development areas. Okay, so such as the interception by trees. Okay, and also the high surface roughness to reduce the surface runoff speed. Okay, and also the surface permeable. What that means, the soil or the earth can absorb the runoff, can absorb the most part of the runoff. Most part of the rainfall. Most part of the rainfall can be absorbed by the earth. And also the roots draw down the groundwater, permit the high rate infiltration. So this process actually can reduce the volume of runoff because the interception, because the absorption, and infiltration, and also can reduce the peak runoff flow rate because the surface, the roughness of the surface, okay, and also delay the peak, delay the runoff peak, delay the hydrograph runoff peak. Now, if we take away the vegetation, so all these benefits are lost. So we will not have all these benefits. So that's why that. So that's why the flooding problems is common in the urban areas in a heavy rainstorm. Because the rainfall or the runoff cannot be drained away quickly. Or the runoff exceeds the capacity of the existing drainage system. So the erosion, the erosion. So that means we can see that if we remove, take away the vegetation, so that means the exposed soils. Exposed soils are easy to erosion and cause a large quantity of sediment to be washed into the nearby waste after heavy rain. And also the carrying capacity. The carrying capacity of the catchment area is reduced because, for example, the interception, the infiltrations means the most runoff will be absorbed, okay, by the natural catchment, okay. But if we remove the vegetation and now change it to the impermeable, if we change the impermeable area, so the carrying capacity of these areas is reduced, and also no infiltration or less infiltration, okay, for the post developed area. So the groundwater recharge is reduced. It means that the infiltration actually is normally used to recharge the groundwater. So that means after the rainfall, so the groundwater level will rise normally, okay. But if there's less or no infiltration, okay, so to the ground, so that means the groundwater recharge is reduced. It's also reduced. And also another impact is the stream morphology. Vegetation actually is very important to keep the stream, to maintain the stream morphology. So many stream or channels are narrow and deep, means the functioning channels and the streams are narrow and deep, with vegetations on the banks. So this vegetation is very important. So the vegetation, for example, the trees can provide the shadings to the water surface, okay, and also can keeping the temperature cool, okay, for example, okay. And also the groundwater can sustain the grass and the trees communities. Means can provide the supplies to the grass, water supply to the grass, trees community. So that means the vegetation, the water body, and the soil are working together. Okay, so this is a functioning ecosystem. Stream, vegetation, and soil. So all this working together functionally. Okay. So if we remove the trees or the vegetations, so the bank erosion will occur. So the stream becomes wider. Okay, so the stream becomes wider and shallower. So the water table will drop. So the water gets hot in summer because no shading, no trees, no shading on surface water. So the water gets hot in summer, so, and also in the cold climate, it may begin to freeze in the winter. So both are the problems. For cool water fish and other species, because water is no longer because the water is no longer freely available on the floodplain, so the water-loving vegetation on the bank will die. So this further weakens the stream banks. Okay, so that means cut down the trees and also remove the vegetations of the streams, so will destroy the ecosystem of the stream. Means will make the vegetation, water, and soil not functioning well. So next one, okay, about water quality. It's okay. So actually, the post-development areas, normally the impervious areas, so with different kinds of the pollutants, okay, such as the bacteria, nutrients, toxicants, sediments, organic matter, etc. And also in the runoff, and also there are many sources of the pollutants. So where are the pollutants come from? Such as smoke from the bushfire. The bushfire is very common in Australia. So every year, so there'll be bushfire in the dry seasons. Okay. So smoke from bushfires, the ash and the smoke from the bushfires, and the dust from the agricultural activities, and also the dust from the roads, and from the industry, emissions from the industry, leaf litter, and the leaf litter, grass clippings, and also other vegetation, and also the linkage and spillage of materials from vehicles and storage tanks, and also the seepage, and also the pollutants from the landfill site. Okay, so all these are the sources of pollutants in the urban areas, in the cities. So actually, the vegetation and also soil are the natural functions as the natural filters for these pollutants. Functions as natural filters of these pollutants. Okay, but if we remove the vegetation and also change the pervious air surface to impervious, so all these pollutants will be in the runoff. So will be in the runoff, and also if we cannot remove these pollutants in the runoff before releasing to the receiving water bodies, so these pollutants will be released to the such as rivers and streams and oceans, cause the pollutions to the water bodies. Okay, so this is the impact of the urbanization on waterways. Okay, so actually you can see the role of vegetations in moderating the runoff of the natural catchment So why the vegetation are important in the natural system, in the natural ecosystem. Okay. This is the so this figure showing the hydraulic cycle, hydrologic cycle. Means this is you can see this is so this is a cycle. Okay, this is a cycle. Okay, so this is a cycle. Okay, this is a cycle. You can see this cycle. So this cycle is repeated. This cycle is repeated. So that's that means we can have the drinkable water. So that's working drinkable water because as we know that over 70% of the surface of Earth are the ocean. Okay, so the water of the ocean it's not drinkable, and it's not drinkable. So actually, this hydrological cycle makes sure that we have the drinkable water. Okay, drinkable water. So the hydrology actually is an earth science. Actually, it's an earth science. Okay. Actually, it includes the occurrence, distribution, movement, and the properties of the waters of Earth. So actually, a knowledge of the hydrology is fundamental to design making process, to the decision making process, where the water is a component of the systems of concern. So normally you can see that the water is transported from the ocean. For the hydrological cycle, the water is transported from the oceans to the atmosphere. Okay. And also then back to the land and ocean. So that means the atmospheric water becomes rain or snow and back to the land and back to the sea. Back to sea. And also for the catchment, for the natural catchment, so the rainfall will becomes the part of the rainfall will becomes the groundwater via infiltration, through infiltration. Okay, but for the artificial catchment, means the impervious catchment. So the most part of the rainfall becomes the surface runoff. So the surface runoff water so will drain away by the drainage network to the permanent surface water stores such as lakes, oceans, rivers. Okay. So we can see that the driving force for this cycle, the driving force for the cycle actually is provided by the sun, actually, by the sun, the evaporation. So the water quality also changed, as we can see. The water quality has changed through the cycle. For example, as we know that the seawater is not drinkable. So the seawater is after evaporation and also rainfall back to the lakes and rivers and also groundwater. Okay, so the seawater can see that through this cycle is converted to the fresh water through the evaporation. And also I just mentioned that the rainfall on the catchment either infiltrate to the groundwater, means the natural catchment, or runs off to the channel, means for the artificial catchment, such as the roads and also the existing buildings or infrastructures. So the urbanization of the catchment actually reduce the pervious areas. So that means increase the surface runoff, Okay. So because the channel streams, have capacity, so if overfilled, so the flooding will result. So that's why the urbanization causes the flooding problems. Okay. Okay, so this is the cycle. So this is the hydraulic cycles, and also how the urbanizations, and also we also introduce how the urbanizations impacts the impact the cycle. So as we know that because the reduced the pervious area, so the most the rainfall become the surface runoff. So that will increase the risk. That will increase the risk of the flooding. So that's why the existing streams or channel systems should be changed or modified to reduce the flooding. For example, we can increase the drainage network flow capacity, increase the existing drainage network flow capacity, and also we can increase the drainage network storage capacity, or we can use the stormwater storage tank using the sponge city concept. You can see the video, watch this video. I just sent you the link about the Happy Valley underground stormwater storage tank. Actually, it functions as a temporary storage tank for the heavy rainstorm. Okay. Okay, as I mentioned that we need to have a break every 50 minutes. Now already 55, so we have a 10 minutes break. Okay. Okay. Hello. Are you still sitting in front of the screen, the computer? Okay, great. Now we just have a break. Okay, we just have a break in the back at the 3 o'clock 5. Okay. Okay, drink some water. Okay. Okay. So after the break, so we move on. Okay, we just introduced the hydraulic cycle and how the organizations impact the hydraulic cycle. So now this slide is showing the water quality cycle. Water quality cycle. Okay. So we can see that the pollutants. Okay, so we have different pollutants. So you can see the different pollutants. So here, okay, so the for example, the phosphorus, nitrogen, metals, and organics will becomes the groundwater. Will be in the groundwater, okay, due to the infiltration, and the gross pollutants and the suspended solids and the BOD, biological oxygen demand, and also others, phosphorus, nitrogen, metals, and bacteria, and also viruses also through the drainage channels. Okay, through the drainage channels. So the phosphorus and the nutrient, nitrogen, and also the metals, and also the organics infiltrations through the infiltrations to the groundwater, and also the soils can be one functions. Soil can be one functions as a filter to remove the pollutants. So, but the for the pollutants in the surface runoff, so we need to take any measures to remove the pollutants. So the pollutant trapping needs to be done for the surface runoff. The pollutant trapping needs to be done in the drainage network to prevent the contaminations of the downstream water bodies. Stormwater. Here are some major stormwater issues. For example, reducing flood risk, rainfall runoff process, actually that being introduced in the catchment water management, and the draining network flow capacity, urban drainage system. Reducing the peak flow means using the detention basins. So for the drainage water system, for the stormwater drainage systems, so can be divided into different parts for the stormwater drainage system. So such as including the roof and the property drainage, means for the building, for example, and also street drainage, means the roof and the runoff from the roof and the properties will be drained to the street drainage system, and the trunk drainage. So the trunk drainage actually normally consists of large pipes or open channels, and retarding basin or retention retention basin. Actually, it is a temporary water storage basin. So this stormwater storage basin normally used to reduce the peak flow rate. And also the receiving water, such as rivers, lakes, groundwater, or the sea, So for the water quality improvement, the following issues need to be considered, such as the contaminant load estimation, the contaminant transport issues, and the stormwater improvement. Means how to improve the stormwater quality by using the detention basin, by using inline traps, wetland, by using a wetland. Okay. So for the stormwater pollution reductions, the different methods can be used. For example, the development control. So we can think about the improving the water qualities at the planning and the construction stage. Okay, so and a source control means we can reduce the stormwater pollutions by community education, and also the contingency plans for spills and site contaminations, and also the treatment, infiltration, retardation, and also any mechanical devices used. Okay, for example, for litter traps, and also we can also use the basin. Okay, as shown in the slides, stormwater detention basin, and also the inline traps, wetlands, and as I mentioned at the beginning, the water sensitive urban design. Okay. So the quality of the urban runoff so can be achieved by source control and the treatment control. And also the best practice stormwater quality measurement objectives are, so what are the objectives of best practices for stormwater quality measurement? Actually, the objectives are to remove, okay, so 80% of the SS suspended solid annual load, and also remove 40% of total phosphorus annual load. Means 45% of phosphorus removed, and 45% total nitrogen annual load. Okay, so this is the objectives for the stormwater quality measurement. Okay, now we move to the week 2. Week 2 is about the design rainfall. So actually, a hypothetical rainfall event normally corresponding to a specific return period. Means could be from 1 year, 2 years, 10 years, 50 years, or 100 years. So usually the basis for design and analysis of the stormwater measurement systems in input, we have the hydrograph, okay, and output hydrograph. So the hydrograph, left one, okay. So this is the hydrograph, okay. So actually it's the plot of rainfall intensity and time for a specific rainfall event. So this is this one. Now the output normally is the hydrograph. So the hydrograph actually is a plot of flow and time. Flow rate. So that means the y-axis is the flow rate, means in the cubic meter per second, and also the x-axis is the time. Means time is how the flow rate changes with time. The hydrograph is the rainfall intensities and the time, how the rainfall intensity change with time. For example, if it is a rainfall event for 15 minutes, so we can use the 10 minutes interval, for example, from 0 to 10 minutes. So the first is the rainfall intensity. Represents the rainfall intensity from the 0 to 10 minutes. So the second represents the rainfall. The second column represents the rainfall intensity of the from time 10 to 20 minutes. Okay, so the third column is the rainfall intensity from 20 to 30, 30 to 40, and 40 to 50. So what we need is how to change the head graph to head graph. Normally we can get this one. This is the design rainfall event. Design rainfall event. Okay. Normally it is hypothetical rainfall event could be. So how can we convert this height graph input to the hydrograph? So later on we will show you how to convert that. Okay. Normally you can use the time area method. Okay. So we use the method or use a model. Use a model to convert the input height graph to an output hydrograph. So actually, in the hydraulic structure design, normally the design storms are used to estimate the flood peak or the total hydrograph. So the design storm normally depends on the design storm depends on the storm duration. It could be 30 minutes, or 1 hour, or maybe 2 hours or longer. And the mean intensity of the rainfall, the rainfall intensity, and also the recurrence interval of the storm. For example, for a minor storm event, so the recurrence interval could be 2 years. But for a major storm event, for a major storm event, that could be 50 years. And also the design storm also depends on the temporal pattern of rainfall, the temporal pattern. So the temporal pattern means the hydrograph means how the intensity change with time. So the mean rainfall intensity normally obtained from the IDF, from the intensity, duration, frequency curves. This is how where's from. Actually, normally the DST department issue their stormwater drainage manual, planning, design, and management. So the updated version is 2018. So actually, this manual already uploaded to the Canvas. Okay, you can find that out in the Canvas. Okay. Okay. Now this slide is showing the hydrograph of a stream, and also the effect of the storm and the basin characteristics on the hydrograph. This how the storm, the effects of storm on the hydrograph, and also the effect of the basin characteristic on the hydrograph. Actually, the in this figure, the figure A to D. So these four figures, these four figures are showing these four. I think these four charts are showing the hydrograph of a stream flow. Okay, of a stream flow A. So A is showing a permanent stream, hydrograph of a permanent stream, period between the precipitation events. So we can see that actually the hydrograph actually is a base flow hydrograph because the groundwater sustains the flow. So actually this is a base flow hydrograph. Means the A is the here I just said that okay, here the A is the hydrograph of a permanent stream between precipitation events. Now, actually, the B, actually this figure, part B actually shows shows the initial hydrographic changes due to the precipitation, due to the rainfall, okay, due to the rainfall. So actually, the interflow and the ground flow are added to the channel precipitations. Means there's for the part for the figure part B, for the figure part B, actually so there's no direct surface runoff. There's no direct surface runoff. So the rainfall actually change to the interflow and the groundwater flow. Means by infiltration. Means no for the part B, actually no surface runoff. So all the rainfall changes become the interflow and the groundwater flow via the infiltration. So you can see there the ground. So you can see the hydrograph changes. The hydrograph changes from the original, but also still a small change. So part C, okay, the part C actually illustrate the surface runoff becomes a component of the flow. Means the in this case, the interflow and the added groundwater flow are zero. Means no infiltration to the means the no infiltrations. Okay, so that means and also there'll be no extra interflow and added groundwater flows added to the stream. So that means the surface runoff becomes a component of flow. Becomes a component of the flow. So the part D, it means all the four components exist with rainfall intensity. Means the rainfall intensity exceeds the infiltration rate, and also the field capacity of the soil is also reached. Okay, so in this case, so that means that it's normally typical a large storm event. Means the interflow, there are added groundwater, and also there are also rainfall, surface runoff. So we can see that the components for the of the hydrograph of permanent stream include four major components: the direct surface runoff, the interflow, the channel precipitation, and the groundwater flow. There's four major components of the hydrograph of the permanent stream. Direct surface runoff, interflow, channel precipitation, and the groundwater flow. Just to repeat again, so A, for A, so actually only the part A. So let me see again. The part A actually only for a small rainfall. Only for a small rainfall. Okay, only for a small rainfall. Okay, and also no interflow or added groundwater components develops. So only the and also no overland flow. I mean, also no overland flow. In this case, it means there are four components. There are three components at zero. Only one component means this channel precipitation, channel precipitation. So you can see that means there is no change for this hydrograph. So the B, I mean for B, B you can see that means there'll be interflow and added groundwater flow, interflow and groundwater flow added to the channel precipitation. So you can see that means the hydrograph change. So C, C means only runoff, only surface runoff, only surface runoff. Okay. D means C means the surface runoff and also the precipitation, channel precipitation. So for D means all 4 components exist with rainfall intensity. That means the D means their direct surface runoff, their interflow, their channel precipitation, and also their groundwater flows. So that means this the D as normally is for a large storm event case. Okay. Because this figure in the ebook, okay. So I just want to. I'm not sure whether the local tutors explain that clear or not. I explain that to you or not. Actually, means I just to repeat that the A to D actually illustrates the hydrograph of a permanent stream, permanent stream. So actually, the factors affecting the hydrograph shape, the rainfall patterns, means the rainfall distribution with time, and also the rainfall distribution with area, and also the direction of the storm movement. So all this can affect the hydrograph shape, and also the catchment or the basin characteristics also have a impact on the hydrograph shape. So such as the catchment area, the catchment slope and stream slope, and also the natural storage, and also geology, the geology. So E, F, G, H. So these four chart. Okay, so these 4 curves. So these 4 curves actually showing the effects, of the rainfall, and also the basin, on the hydrograph shape, Now for the first two, E and F, the curve for these 2 curves, E and F. So actually, these 2 curves showing the locations, showing the location of the storm, of the localized storm in the drainage basin, affect the time distribution. So we can see a storm, okay, a storm occur in a remote part of the basin, for example, E, okay. So this is the outlet. So this is the outlet of the basin, okay. So we can see that the storm occurred in a remote part, of the basin. So we can see that the runoff at outlet will be longer, and also the peak flow lower due to the storage in the channel. So you can see that means it will take a long time for the peak flow, okay, and also the peak flow also lower, because the part of the rainfall will be stored in the channels, stored in channels. So for the F, so you can see the F. Now for the F, now you can see the location of the of the storm different. So the location of the storm actually is near the outlet of the basin, right? So this storm, you can see that is located very near the outlet of the basin. So we can see the hydrograph shape different. Different. So we can see that the the peak flow occur very quickly. Very quickly. Means it takes short time to of the peak flow. So the peak flow occurs very quickly. Okay, compared to E. And also what? And also the peak flow is higher. Okay. Okay, and the peak, we can see that peak flow is higher than E. Okay. So this is the E and F. So how about G and H? Let's look at the G and H. These two. Compare these two. So for G and H, so actually it's about the shape of the basin. So how the shape of the basins affect the hydrograph shape. So you can see that for G and F, there are the shape of the basin different. Okay. So because the shape of the basin influence the time for the water from the remote part of the catchment to the outlet. Okay, so the occurrence of the peak and also the shape of the hydrograph will be affected by the basin shape. Broad shape at outlet, for example, G for the G. For the curve G, for the G curve. So we can see that the outlet at outlet, so the broad shaped. Okay, the broad shape. So the broad shape outlet, at outlet, so will result in the peak flow occur very soon. So my peak flow occur very soon, because the less time of the concentration. Okay, it is very easy to understand, right? The broad shape at the outlet, so that means concentration time will be very short concentration time. So that means the peak flow occurs quickly. And a narrow hydrograph with a high speed means the peak is higher. Okay. And now the curve in the H, so the narrow shaped outlet. So that means you can see at outlet the shape is narrow. Okay, narrow shaped at outlet. So the peak flow occur at a long time because it takes a long time of concentration. It takes a long time of the concentration. So that means that the peak flow occur at a longer time. And also the lower peak hydrograph, and also the peak is lower because the storage in the channel. Okay. So actually, I spent time to talk about this this figure. Actually, this figure actually are helpful to understand the storm, the effect of storm, and the basin characteristics on hydrograph shape. Okay, so the curve A, B, C, D represents or illustrate the hydrograph shape of a permanent stream. Okay. And also there are four major components of the hydrograph for a permanent stream. So direct surface runoff, interflow, channel precipitation, and groundwater flow. And the curves from E, F, G, H represents the location of the localized storm, and also the basin shape, the effects of the location of the storm, and also the basin shape on the hydrograph. And also, I just mentioned that the geological characteristics also have impact on the hydrograph. Okay, so the geological characteristics include, for example, the surface and the subsurface soil type, for example, rocks and their permeabilities. Okay. And also the geological characteristics also influence the infiltration and percolation rates. So the runoff will be more for low infiltration capacity soil than for high infiltration capacity soil. So that means the surface runoff will be more. So there'll be more surface runoff for low infiltration capacity soil. Okay, so this is the effect of the storm and the basin characteristics on hydrograph shape. So if you have any questions. Okay, I move to the next slides now. This slide is showing the, I just mentioned that the factors affecting the design storm. Okay, so that means there are following factors the design storm depends on. Okay, in design of hydraulic structures, design storm are normally used. Okay, to estimate the peak, flood peak, or the total hydrograph. So the storm, the design storm actually depends on the duration of storm, the intensity of the rainfall, recurrence interval of storm, and also the temporal pattern of rainfall. Okay, now these slides, actually this figure actually is from the Drainage Services Department, the stormwater drainage manual, Okay, so actually I think this is update version, 2018 version. Actually, this is it's called the ADF curves, ADF curve: intensity, duration, and frequency, So you can see the duration, the x-axis is duration, the y-axis is the intensity, extreme mean intensity, extreme mean intensity, and each curve represents the frequency, or they represent the what occurrence. Occurrence means the recurrence, average recurrence interval. ARI, the average recurrence interval from 2 years to 1,000 years. From 2 years to 1,000 years. Actually, I also get some information from this menus actually to share. I can share here. So actually, the development of the ADF curves for any location in Hong Kong actually given in the menu. And actually, these curves are most useful tools for the engineers, especially in the design of water resources. Actually, the ADF relation actually is based on the GV distribution model. It means based on the generalized extreme value distribution model. Okay. The rainfall for the update menu from update version. So the rainfall statistics at Hong Kong Observatory headquarters are recommended for general applications. For general applications, normally we use the Hong Kong Observatory headquarters data or statistics, rainfall statistics, except time motion area, West Lanto area, and the North District area. Okay, so that means for general applications, normally we use the Hong Kong Observatory headquarters rainfall statistics. Okay, so as I mentioned before, that means the mean annual rainfall, in Hong Kong from 1981 to 2010 in Hong Kong is about 2,400 millimeter. So, but however, there are some variations. Okay, for example, Tam O Shan, higher annual rainfall, more than 3,000 millimeters. Okay, more than 3,000 millimeters, and some area, such as North District, a relatively lower annual rainfall. Okay. So that's why the rainfall statistics at Hong Kong Observatory headquarters are normally used. So ARI. Now, next I will talk about the ARI, the average recurrence interval. So the ARI actually is the average or expected value of the period okay, between exceedance of a given precipitation or discharge. This usually expressed in a year, in years. Okay, it is also called return period. So actually, the return period is selected on the basis of the economic efficiency or the protection needed. So that means if you select a larger return period, so you need to have a higher cost. You will have a higher cost for design of the drainage systems, urban drainage system. Okay, so that means you need to have a balance. So typically, for the urban drainage system design, 2 to 20 years return period. 2 to 20 years return period. And also this figure showing the ADF curves of Hong Kong Observatory headquarters for durations not exceeding 4 hours. Means not exceeding 4 hours. Okay. And for duration exceeding 4 hours, so the rainfall depth instead of the intensity is used. Means if the duration is exceeding 4 hours, now we will not use the intensity. We will use the rainfall depth. So the rainfall analysis actually is based on the historic or synthetic rainstorm. Means the historic, okay, based on the historic rainstorm data. We can also based on synthetic. So historic rainstorm are normally used in the flood investigation or model calibration. That means this for the flood investigation or the flood prediction, okay, or the flood evaluations, flood flow predictions. Normally we use the historic data, historic rainstorm data. For planning and design of drainage systems. So how about the planning and the design of the drainage system? So normally the synthetic rainstorm are commonly used for the design, the planning and design of the drainage system. And also for the design purpose, the synthetic rainstorm are normally based on Gumbel distribution, okay. So the historical rainstorms are used in the actual storm event simulations, so which carry out with the calibration, verification of the hydraulic models, with flood forecast and also post-event flood evaluation. And also in Hong Kong, actually there are around 200. So from the manual, from 2018 manual, so there are 193 rain gauge seditions in Hong Kong. I think there are more rain gauge stations in Hong Kong, maybe around 200. So actually, normally the historic data can be collected from this stations, from these stations. Okay. So about the synthetic rainstorm, I just mentioned that the synthetic rainstorms are normally used to simplify. Why we use the synthetic rainstorm for planning design? Because it is used to simplify the planning, design, and the management of the stormwater drainage systems. So the artificial design storms, okay, the artificial design storms are built upon the historical rainfall records. Okay, this means the synthetic rainstorm actually based on or built on the statistics of the historical rainfall records. So that's why we need the stations, the rainfall gauge stations, So this rainfall, so these gauge stations you can use to collect the rainfall data, okay, in different areas, and also that this data can be used to, for example, to develop the synthetic rainstorm or artificial design storm. Okay. So this is the IDF curve. IDF curve actually very important. Okay, for the design storms. Okay, for the design storm, for planning design of the storms, and also very important for flood predictions and flood evaluations, and also calibrations. Okay, so this is IDF curve. So and also this slide is showing the a simplified IDF curve. So the IDF data can be used the following equations for easy applications. Okay, actually, this is only for easy applications. It's only for easy applications. Okay, so. So this equation, you can see that actually will depend on the parameters. Three parameters will depend on the three parameters A and B and C. Different three parameters. So these three parameters will be different. With a different return period. 2 year, 5 year to 1,000 years. These three parameters will be different. Okay, will be different. Okay. So that means in the calculations, you need to firstly determine the return period, and also select the appropriate ABC parameters. And also the duration of the storm, duration of the rainfall. Normally, for the urban drainage design, the time of concentration normally is used as the duration. Means the travel time of the runoff from the remote pond to the catchment outlet. So factor. Okay, for large catchment, so the area reduction factors are used. The the area reduction factor are used to estimate the area rainfall of the same ARI from pond rainfall. So how to get the RF? Actually, this is from the also from the menu. This is from the menu. Okay, so less than 25 square kilometer. So the ARF is 1. Okay, so if the catchment area is larger than 25 square kilometers, so the factor, the reduction factor, can be calculated by use this one, by use this formula. But you can check that in the e-book, in the e-textbook, or in a lecture, paper slides. So actually, normally this factor is less than 1, if the area larger than 25 square kilometers. Okay, so this is the spatial distribution of the rainfall. So this slide showing the temporal pattern. The temporal pattern means how the rainfall intensity change with the time. So here you can see that it will show you the height graph. The different height graph will result in different hydrograph. So normally the rainfall does not fall with a uniform intensity. Means the intensity will be also changes with time. So the behavior of the runoff hydrograph will be affected by the temporal pattern of a storm. So this figure showing how the hydrograph affected by the temporal pattern. So can different hydrograph will result in different hydrograph. So in the design, the same temporal pattern is normally used over the entire catchment. Okay. So the degree of variability of intensity in the pattern, okay, normally affects the magnitude of peak of the hydrograph. Okay. So the hydrograph shape depends on the rainfall pattern. So you can see how the temporal pattern, how the temporal pattern affect the hydrograph, So this one you can see that the high intensity at the early stage. Okay. So you can see that the peak occurs very quickly, and the peak rate is higher because the intensity is higher. Okay. This one actually is quite is broad. So you can see the hydrograph is broad because the intensity, the variation is the variation of the intensity is not too large. Okay. So this one actually the high intensity at the late stage, so that means you can see that the peak flow occurs. It takes a long time to for the peak flow. Okay, now it's 3 o'clock, 55. So we take another break. Okay, take break. Hello. Okay, back around 4 or 5. Okay. Okay, after the break, we move on. Let me see. This is showing the for the runoff estimation. Normally, actually, this is also from the stormwater management manual from the DST. So actually, for the runoff estimation, normally we use the rational method. Okay, later on we will introduce we talk about the rational method. So for the rational method, actually, a uniformly distributed rainfall with the intensity determined by IDF regime should be used. Means that for the rational method, normally we use the intensity from the IDF curves. And also for other methods of runoff estimation, and for storm duration shorter than 4 hours, actually normally symmetrical distributed rainfall is recommended with following formulations. Means for other methods, these are for other methods. So this slide is also showing the for other methods. For other methods, okay, this is all showing the means this one, okay, the runoff estimations, for other methods, Okay, this is also from the manual, actually, you can see these are different. We use the this is called synthetic rainstorm profiles. Okay, and also they also use the 3 parameters. To determine the rate of rainfall. Okay. Let me see. Okay, next about the rainfall about runoff from design storm. Okay, normally we will select the appropriate ARI for the project to get the IDF rainfall. Select the average recurrence. For example, I just mentioned that. Okay, so actually select the ARI of a design storm. Actually, normally we have some factors for considerations. Okay. For example, the type of structure or the area of the land area affected by the flood. Okay, and also how the catchment storage can delay the flood peaks. Okay, and also the sequence of failure. Okay, a direct and indirect results on structures and downstream areas if overtopping occurs. Okay, now here I receive a question from the Alex. When we calculate the design rainfall profile, the value of rainfall is maximum near the 0. Is this mean that we shoot out the rainfall reach the maximum intensity at the very first time period? Why the rainfall maximum near with the value of a rainfall maximum near the 0? You mean this figure? You mean this figure? You mean this figure? Okay. Yes, this is symmetric. This is symmetric. Okay. So actually, it is assumed that this intensity. This intensity actually is symmetric. You can see that for example, if you want to calculate the time, if you want to calculate the time in the 20, for actually in the 40, in the rainfall pattern is 40. Rainfall values is 40 minutes, 40 minute durations, 40 minute durations. So normally we'll take well, how can we get the data, get the value of the rainfall from this figure? If we know the return period, for example, 2 years. For example, if 2 years, normally we will take the 20. Here, this value, because it's symmetrical. Symmetrical means from left it's minus 20 minutes, right is 20 minutes. So that means normally we take this value for this intensity. So normally this is a synthetic rainstorm profile. So normally we assume that the rainstorm not is at the zero. It not means that the maximum is near the zero is maximum. Normally we assume that means is at the middle of the rainfall is the maximum. Actually, it is also based on the let me see, based on the distribution. I think it's based on the I think it's based on the Gumbel distribution. So actually, we assume that this rainfall storm is symmetrical. Okay, symmetrical. So that means the maximum rainfall will be at the middle of the rainfall. For example, if there are 20 minutes rainfall event, so the maximum rainfall happened at the mid 20. Is that clear? Okay, so that means the zero now means the time. Now means the time, the start of the rainfall event. Now means the start of the rainfall. Okay, actually, so actually we use the symmetrical method to represent the rainfall profiles. So if we take, for example, if we want to take a 40, as I mentioned, if we want to take a for a 40 minutes rainstorm, so normally we will take the value 20 minutes here, 20 minutes, because it will be from the mid of the rainfall to the end of rainfall is 20, and from beginning to the mid of the rainfall is 20. So total with 24 minutes. So for 40. So for 40 minutes rainfall rainstorm. So normally we will use the value here for 20 on each side. For each side for 20 minutes, because we assume that the rainstorm maximum is maximum at the middle of the event. Okay, not at the very beginning. Normally, because we assume that at the very beginning of the rainstorm, the small raining and then become bigger and bigger, and also at the mid time, for example, after 20 minutes, the rainstorm the maximum, and then after the 20 minutes, the rainstorm becomes smaller and smaller. Okay, so that is the normal. Normally, it's a normal pattern of the rainfall. It's also called synthetic rainfall storm. We assume that. Okay, is that clear for you? Okay, let me see. Now, as I mentioned that there are different factors we need to consider to select the ARI, okay, interval, the average recurrence interval. And also such as the catchment storage, the consequence of failure, and also the cost, and also future development work in the catchment. So typically 2 to 5 years for the pipe system in the urban drainage in the urban drainage design. So if the down area, so the downtown area of a city is a part of the drainage system, so then we use 20 year. But for important structures, for important structure of facilities, for example, so if the hospital or power station to be protected at the downstream, okay, if a hospital or power station downstream is to be protected, so we may use a larger ARI, for example, 100 ARI, average recurrence interval. So in many cases, the geography and the finance availability may influence the choice of ARI. And also some local factors and also influence the choice of ARI. Okay. And also, as I mentioned, that the ADF curves is only valid for the area 25 square kilometers. Okay, so that means if the catchment area is larger than 25 square kilometers, you use the error reduction factor. Reduction factor. So the temporal patterns can be get from the ADF rainfall, and also for the symmetrical rainfall profiles. I think I think in the assignment 2, actually, I think you will use that. Okay, to you need to design the rainfall profile. Okay, you need to design the rainfall profile for different durations. Okay. And also, we also need to consider the losses of runoff. Okay, losses of runoff. For example, the infiltration, evaporation, interception, the surface storage, surface detention, channel detentions. Okay. Okay, design the urban drainage systems. Okay, so actually, to estimate the flood magnitude and also volume of the stormwater from a storm, so there are actually many methods, many different methods. Okay, but here we actually introduced 2 methods. So one is the rational method. So the rational method actually used to estimate the peak discharge from a temporal uniform rainfall exercise. Okay, so that means the rational method that we will use to estimate the peak discharge. So, and also another method is the time area method. So the time area method actually will generate the flood hydrograph from temporally varying rainfall exercise. Means to get the flood hydrograph from the hydrograph means the temporal rainfall pattern. So the 2 methods we you introduced. Okay, for estimate the flood and also the volume of the storm water. Okay, so the rational method used to estimate the peak discharge. Okay, and also the time area method will use to generate the hydrograph. So with the hydrograph, we can have the volume. So we can get the volume of the storm water. So then the area under the curve, the area under the hydrograph curve is the volume. It's the volume of the storm. So week 3 we talk about the rational method. Actually, rational method actually is very easily to apply because it is very easy. Okay, easy to apply. So here is the equations for the rational method, the formulas for this equation for the rational method. So the rational method I just mentioned actually normally is used for the estimation of the peak flow from small catchments. from small catchment. As mentioned, 25, less than 25 square kilometers. So estimate of this flow rate can be used to storm water drainage system, means size and the slope of the pipe systems, and road works such as design of the covers, small medium bridges and the causeways, and also the farm and the rural works, farm dams, and the soil conservation measures. So here you can see that the peak flow rate can be estimated by using this rational method. Okay, F here is the conversion factor to balance the units. For example, for the area, so you may use different unit. For example, you can use the kilo square meter, square kilometer. So the F is the 0.278. So you can use the hectares. So F is the 0.00278. And C represents the runoff coefficient. Okay. So the A is the I is the intensity. The intensity is from the IDF curve. Okay. The average rainfall intensity. So this intensity is from the IDF curve. So the A is the area of the catchment. Okay, and the T is the time. Time is the concentration. And because I just mentioned that the time by the rational method, okay, the time of rainfall actually is the time of the concentration. Means the time taken for the water particles to travel from the remote pond, from the furthest pond, from the remote pond to the catchment outlet. Okay. Now, rational method actually there are assumptions, advantages, and limitations of the rational method. Assumptions, okay. Actually, the first assumption is that the rainfall is uniform intensity over the whole catchment for the duration of the design form of the design storm. Means for the duration of the design storm, actually the rainfall is uniform intensity of a uniform intensity over whole catchment. Means over the whole catchment, the intensity have the same intensity. And the second assumption is the critical duration of the rainfall is equal to the catchment's time of concentration. Means the critical duration. Because to determine the peak flow, we need to know the critical duration. The critical duration of the rainfall actually is the catchment time of concentration. So the third assumption is the average recurrence interval of the peak charge is equal to that of the rainfall intensity. So that means the average recurrence interval of the peak discharge actually is equal to the rainfall intensity. Okay. So there are many. There are also some advantages of the rational method, such as the simple to use, as I mentioned. Okay, and also you can format as a spreadsheet on the computer. Okay, we format that on a spreadsheet on a computer, and no observed data is needed. Okay, and a lot of experience actually about its applications available. Means there are also applications of its experience. So but actually there's also some limitations by using the rational method. For example, it's only for the small catchment, as mentioned, less than 25 square kilometers. Okay, unless a lot of recorded data is available to derive the statistical parameters for use in medium catchment. So that means we need to get more data. Okay. Peak flow rate, okay, is the only output. Means we can only get the peak flow rate by using the rational method. And no allowance is made for the catchment storage effects, such as surface storage, the detention. Means all the means no channel or detention or surface storage no allowance is made for the catchment storage effects. Means the surface runoffs will becomes the all the surface runoffs will be become these outflow, become outflow. So the rational method actually is only applicable to small catchment. Okay, now here I have a poll for to check your understanding. Okay. Let me see a poll. Okay, so I have a poll. So let me see your understanding of the rational method. Yes, I just mute my mic and waiting for the poll. Okay. Okay. Now I see the 19 students. 19 students give their options for this poll. Actually, the answer actually, as you know, I just mentioned that, okay, the 25, okay, 25. So the rational method is only valid when used for small catchment area less than 25 square kilometers. Okay. Okay, I'm not going to wait. So the rational method, the steps for the rational method. Okay. So step one, select the ARI for which design discharge is required. Normally, and also I just talk about the factors, okay, affecting the ARI. Okay. For the AI selections, normally for the urban drainage pipe design normally could take 2 to 5 years. Okay, if the downtown area of the city is part of the drainage system, normally we take 20 years. But if we have some structures to be protected, for example, the power stations, normally we use 100 years AI. So the step 2 actually is the measure of the catchment area. Okay, so normally it is normally valid for the area less than 25 square kilometers, and also we can get the runoff coefficients. Means different surface characters will have different runoff coefficient. Okay, so the surface such as asphalt, concrete, brick, actually normally they have a higher runoff coefficient. Means what that means. So that means the most the rainfall becomes runoff, becomes surface runoff, becomes runoff because the impervious most are impervious area, most impervious area. For the grassland, you can see that they have a lower runoff coefficient. So that means the most runoff absorbed by the soil, absorbed by the soil. So only a small percentage become the surface runoff. So this is runoff coefficient. And also for the ARI, other than 10 years, the runoff coefficient now can be increased. For example, for 20-year ARI, increase 10%. For 50-year storm, increase 20%. For 100, normally increase 25%. So as I just mentioned that when select the ARI, the average recurrency intervals, we need to consider location and type of structure, consequence of the flooding, economic considerations, and the maintenance requirement, and the interruptions of the traffic interruptions due to the excessive flooding. Okay. Step 3, after get the coefficient, step 4, we determine the time of concentration, TC. For time concentration, actually here you need to we spend a bit time to talk about the time of concentration. Okay. Actually, the time of concentration actually not consist of the time overland, means surface runoff time, TO, and also the channel time or gutter time, TCH, and also the pipe time, TP. TP. That means that the time of concentration actually has three different components here. Okay. So. And also for the design of any urban systems, so the minimum T, the minimum time of concentration, okay, for the flow from the first inlet pit should not less than 5 minutes. Okay. And now for overland, first let's look at the overland. For the overland flow across an even surface to the road channels such as parks, gardens, roads, we can use this formula. Okay, we can use this formula. Okay, so this one. Okay, use this formula. So we can use this formula to get the overland concentration. And also for the time flow in the channel or the gutter, we use the Manning's equation. We use the Manning's equation. Okay. But actually, we may let first how to get the overland, time concentration. Now, actually, by using this formula, actually, you cannot get the TC. You cannot get TC directly. So normally we prepare a table of T and T times I, 0.4 power of I, 0.4 power of I. Okay. we get a table. So we get a table of these two. And also, of course, this from IDF curve. So then we can have we know the L, the S, and also the N to calculate the TI, to get the value. So the L is the flow path length. So the S is the slope. So the N with asterisk, actually the surface roughness. It's a surface roughness. Okay, it's not the Manning's N value. So I did this is different with the Manning's N value. So the N is about the roughness, surface roughness coefficient. And you can get that from this table. You can get this N from this table. Okay. So with the LSN, this one with LSN, you can get the T times I 0.4 power value. So you can get the corresponding T and I from the table, from this table. First, you get the table. Then you calculate the value, and then you get the time. So, so this example of the table. For example, we get the intensity. So we get the intensity. We get the intensity from the IDF curve. So 2 years and 5 years. Okay, for different durations. Now we can get the T times I 0.4 power. Okay. So this value is the T, the time T times the I 0.4 square. So we can get this one. Okay. So we have this table. After we have this table, we can calculate the in a particular design. In a particular, we know the L, we know the S, we know the N. So we can get the T times I 0.4 power. Okay. So for example, if the value is this one, if the value is this one for 5 years, so we can find out the time of constraint is 7 minutes. 7 minutes. So that means this is the method to get the overland time of constraint. So that means you cannot get this directly from this formula, but you can use these steps to prepare the table, to get the T, to get the value of this one, and also find out T from the table. Any questions? Okay. Now determine the concentration, the time of concentration. So for the channel flow, for the concentration time, for the channel time, for the time of concentration in the channel time or the gather time, we use the Manning's equation. This is the Manning's equation. So firstly, we get the V and get the velocity, and also the L over the velocity. We can get the time, the channel time. So R. So here. I think you can get the more details about this parameters from the E textbook. The R actually is the the R is the hydraulic radius. The hydraulic radius actually is the cross section area. Means the wetted cross section area of the flow divided by the wetted parameter. Means the cross section area of the flow divided by the wetted parameter. So S is the slope of the channel of the gutter. So N is the Manning's N value, Manning's roughness coefficient. So be careful here. The N is different with the previous N. Okay. So in this equation, you can see there's also N, N with the asterisk, the N with the asterisk. So this is the surface roughness coefficient. So for Manning's, equations, there are also there's an N. So this N is the Manning's roughness. It's called the Manning's roughness coefficient. So this Manning's roughness coefficient is not dimensionless. Means that it have units. So this N has units. It's cool. Actually, the unit is the time over the length 1/3 power. 1/3 power. Okay. So the magnings and value are often selected from tables, but can be also calculated from the field measurement. So next is about the time in the pipe. So the time in the pipe, we normally use the Darcy-Weisbach equation. Darcy-Weisbach equation to get the time, in pipes. Okay. So we use the Darcy-Weisbach equation here, so we can get the velocity. Okay, we can get the velocity. So after we get the velocity, so we can get the time. Means the length over the velocity is the time. Okay. So here the F is the friction factor. Actually, this factor actually is from the Moody diagram. So the H is the head loss along the pipe. H is the HL is the head loss along the pipe. So L is the pipe length. D is the diameter of the pipe. So G is the gravity acceleration. The gravity acceleration 9.81 meter per square second. So this is the rational method how to determine the time of concentration. So actually there are two. There are three. There are three times you need to calculate three different time of concentration. So one is the overland runoff, so the second one is channel time, and also the third one is the time in the pipe. So step 5, so determine the I for duration T and ARI for Y years. Means if the duration time we know, and also the ARI we know for 2 years. So means after getting the time of concentration, so we can get the I from the IDF curve. Here's a question about the SF. SF now represents the slope of the pipe. Okay. Normally represents the slope of the pipe. Okay. Yeah. Okay. Okay. Now step 5, we determine the I, the intensity, rainfall intensity. So normally for the rational method, we determine the rainfall intensity from the IDF curve. Okay. So now we know the time of concentration, right? We know the time of concentration. So for example, the time of concentration is 10 minutes, and also we already know the ARI, for example, 2 years. Okay. So we can get the intensity. We can back to the curve. Let me see the curve. This one. Now for the rational method, we use the IDF curve. For example, it is for example, duration is the time concentration. For example, if would be maybe it's 0.5. Okay, we calculate the concentration with 0.5 hours. I mean 30 minutes. So it's a 2 years interval. We can get the intensity here. It is maybe 230. 230. Of course, you can also use that to calculate here. Okay, you can also use that to calculate the intensity by using this equation. To calculate by using this equation. Okay. Okay, then now we know the AF, C, and I in the area. Now we can calculate the peak discharge. So here, here's some kind of the notes. I think a typical urban drainage scheme has a number of subcatchments. So each has its own TC and I. Means, for example, we may have some, for example, 2 or 3 subcatchments. Each catchment, the area will be different. So the concentration time will be different. So the I will be different. Okay. So the design capacity of the gutter, inlet, pit, and pipe is based on the peak flow. It's based on peak flow. So for gutter and the inlet pit, so if we only have one subcatchment, so the TC for the area is used. For that area is used. So for the pipe, which may have flow from a number of subcatchment, for example, this pipe will have the flow from the two different subcatchment. Okay, so the time or the concentration of the whole area involved must be calculated. Normally, the time of concentration is the time of concentration is the highest one. Means the highest concentration time of the subcatchment normally used. Now, actually, this slide is talking about the steps in design analysis. Okay, design analysis. So, for example, now for normally the preliminary layout of the drainage system. So that means the subcatchment, the pipe networks, the major flow roads, and then we need to estimate the manner system design flow rate for the pipes and pits by using the rational method. And also we develop the specification of the pit inlet types, calculate the capacities and also the acceptable flows. And then we need to calculate the major flow rates, and compare with the capacity of the roadways and other major flow routes. For example, for the manner system, we may use the AI, for example, for 2 years. For a major flow rate, or we can say use a 20-year AI. So we use the hydraulic calculations to determine the pipe size and to fix the pipe inverts. Actually, we'll introduce that later. With the allowance for cover and the minimum slope required. And also we need to check the HGL, the hydraulic grid line, okay? And also working upstream from controlling and receiving the water levels. And also there are some kind of for the hydraulic design, actually there are some kind of the information that can provide it. I think from the menu, okay. So for example, the spacing of the pits, okay. Spacing of the pits should be designed. For example, in Hong Kong, the maximum design for the pit spacing should be limited to 25 meters. And also for the pipe drains, also there are also many requirements for the pipe drains. For example, straight lines between the pits. So that means the pipe should be set in straight lines between the pits. Okay. And also to be designed to flow as open channel. What that means? It means no pressure, no pressure at open channel. It means no pressure. Okay. And also have a minimum diameter 150 millimeters. Means the pipes normally have a minimum 150 millimeter, and also have a specified depth. So that means the cover. Okay, the cover. So the cover actually from the surface of the carriageway to the top of the pipeline is 900 millimeters. Minimum, the minimum cover. So that means the minimum cover from the surface of the carriageway is 900 millimeters. For footway, the minimum cover is 450 millimeter. And also the slope, normally the minimum slope is 100%. Is required. And also the hydraulic grid line, the HGL, the hydraulic grid line. Normally also require the hydraulic grid line is the is coincide with the upper vert or inside top of the pipe, no pressure. So that means the hydraulic grid line is the same with the upper vert. the hydraulic line is the same with the coincide with the upward of the pipe, and no pipe diameter should be less than the diameter of an upstream pipe. So that means downstream pipe diameter should be equal or larger than the upstream pipe. And also the velocity actually should be less than 5 meters per second to prevent the erosion of the pipe surface. It means if the water flow is the velocity of the flow is high, so actually it will speed up the erosion of the pipe surfaces. And also the velocity of the flow should be also larger than 0.5 meters. Means not too high and not too slow, not too high, not too slow. Okay, larger than 0.5 meters per second to prevent any blockage. So there are some kind of the requirement for the pipe drains design, the pipe drains design. So here is one example. Here's one example. Apply the rational method to design for a typical urban drainage design, and also, so we can see that this urban drainage system has a number of subcatchment, parkland, paved area, residential area, and paved footpath and court. Okay, and also each subcatchment has its own time of concentration, so has its own rainfall intensity. For example, the parkland time is 25 minutes, and the time of concentration is 25 minutes. So the paved area, the time of concentration is 8 minutes, and also the residential area, the time of concentration is 15 minutes. Okay, so that means the times of concentration are given here in these examples. Okay, so but in some cases you need to calculate. Okay, and also this drainage design actually is designed for a minor storm event for 2 years return period, and a major storm event for 50 years. And also the time of concentration, and also the surface roughness coefficient. Surface coefficient of C is given. It's given. Okay, so actually this question is actually you need to determine, okay, the flow, okay, to each pit, okay, the runoff flow to each pit A, B, C, D, and also you need to determine the pipe AB, the pipe AB, pipe BC, and the pipe CD. Okay. So now, firstly, you need to get the intensity. Normally, we use the rational method to use the rational method to estimate the peak runoff, to estimate the peak runoff. So for the rational method, actually, we normally get the runoff. Get the intensity from the ADF curve. Okay, so that means from the also you can calculate by use the equations. Okay, so here list the time of concentration, and also the intensity, and also the ARI list and table. So that means if you know the times of concentration, you can get the intensity from this table. Okay. For example, 25 for the parkland. The parkland is 25 minutes, so you can get the 2 years and 50 years intensity here. 2 years is for 25 minutes here, and also the similar for other for 80 minutes. 80 minutes here, 80 minutes, and the 15 minutes. 15 minutes is here between the 14 and the 16. Of course, you can calculate it by using the equation. Okay, now we have another break. Okay, so we let me see. I'm breaking now. So back 5:05. Okay. Hello. Okay, I'm breaking the back at 5 o'clock. 5 Okay, after break, we'll move on. Let me see. Okay, so firstly, the time of concentration for each subcatchment given in this example, and also the there are 2 storm events required for this example, 2 years AI, and also for the minor rainstorm, and also for a major rainstorm 50 years. So we can get the intensity, rainfall intensity from this IDF table. Okay. So next, you can use the rational method to calculate the flow. Okay, to calculate the flow to each pit. Okay, from the A, B, C, D. There are 4 pits. Okay, so you need to calculate the runoff to each pit. Now here we can see that the for example for the pit A, so the time of concentration is 25 minutes. Okay, so and also for the intensity we get from the IDF curve or table list here. Okay, list here. I have it's here. So and also the we also need to get the C, the runoff coefficient, C, and also given runoff coefficient also given C. So we can get the effective area. Okay, equivalent impervious area, EIA, equivalent impervious area, EIA, means C times A area. This one. And then the sum of EIA, because the for pit for example for the pit D, for pit D actually it includes 3 3 subcatchment flows to the pit D. So that means we need to take sum of each EIA of EIA. So by using the rational method, you can get the peak flow. Okay, for 2-year ARI and also for 50-year ARI. For example, for the pit A, you can see that the for 2-year ARI, so the peak flow is 2.41 liter per second, and for 50-year the peak flow 4.15 liter per second. So this is the calculations for pit A. So the pipeline flow, time of concentration 24 minutes, and also the rainfall intensity, and also using the rational method, so we can get the peak flow. So similarly, so we can get the peak flow for the pit B, for the pit C, and the pit D. Now be careful for the pit C. For PC, actually, there are 3 catchment. Maybe we move to the previous one. 3 catchment. 3 subcatchment now contribute to the pit D, the residential area, and the paved footpath, and the court. So you can see each subcatchment they have different time of concentration. So in this case, we use the longest times of concentration. Means the time concentration. For example, the residential area is 15 minutes. From the court, 5 minutes. Okay, and from the pavement is also 5 minutes. Also 5 minutes. So we use the longest time concentration. So that's why here you can see the longest time for the D, for the PD. So for the area, so for the equivalent purpose area, actually there we should include the 3 area. So finally we can have the peak flow to the pit D for the PT. Okay, next we determine the pipe. So a minimum 150, minimum 150 diameter pipe will be used. Okay. So for the pipe design, okay, take the flow from the pipe line is 2.41 liter per second. Means for the pipeline, so the peak flow to pit A, so we just calculated is 2.41. And also we can see that for pipe AB, only the runoff from pipeline, right? Okay, for the pipe AB, only the runoff from the pipeline. Okay, so that means the peak flow is 2.41 liter per second. So you assume that the pipe has the same slope of the root surface, 1%, and also this is also the requirement of the minimum slope. Okay, slope. So the pipe diameter of we can try the 150 millimeter. 150 millimeter. Okay. So the key is 0.15 millimeter. So the concrete pipes have a key 0.15. So this is the surface roughness. This is absolute value. This absolute value. As you can see, they have a unit. And also the diameter 150 millimeters. So the friction factor is 0.02 for fully turbulent flow. So this can be get from the Moody adjustment Moody diagram. So by using the for the pipe we use the Darcy-Weisbacher friction equation for the pipe flow. So we can get the velocity here. Okay. So because the S is slope 1%, D is diameter, F is the friction factor 0.02. So finally we can get the velocity. So we can get the velocity in the pipe. Get the velocity in the pipe AB. 1.212 meter per second. Means the capacity. This is the capacity of this pipe. Okay. So we can get the pipe flow capacity, the area times the velocity. So we can get the capacity of the pipe is 21.43 liter per second. Okay, per second. So because we just calculated the peak flow in the pipe AB is 2.41 liter per second for 2 years AI, and also for 50 years is what? For 50 years is 4.15. 4.1. Okay. So actually that means this pipe is suitable. Okay, because the capacity is 21.43 liter per second, and much larger. Higher than the peak flow for 50 years. Okay, 50 years is 4.15 liter per second for 50 years. Okay, of the major event flows. So that means this pipe is suitable. Okay. Okay, next to the pipe BC. Now for the pipe BC, actually the drains both the parkland and the paved area. So for the pipe BC, you can see that the pipe BC drains the paved area. Okay, means from the pit B, and also drains the runoff from the pipe AB. Okay. So we can estimate the flow time in the pipe AB. The flow time in the pipe AB is the length of pipe over the velocity. We just calculate it's around 0.5 minutes. We just assume around 0.5 minutes, so we can get the concentration. For the pipe BC, we can get the time of concentration is 25.5 minutes. Okay, so we can get the intensity from the table, IDF table. So we can get the using the rational method, so we can get the peak flow. So you can see the peak flow is 8.27 liter per second. So that means it's still okay, all right? Okay, the 150 millimeter diameters, the pipe is still okay because the capacity is 21.43. The capacity 21. The capacity 21. So that means it's still okay. So similarly, so we can calculate the pipe CD. Pipe CD, you need to calculate the runoff from the paved footpath and also from the BC. The flow from BC. And also for DE, for the pipe DE. So that means you need to calculate the runoff from the residential, from the paved footpath, from the core, and from the CD, the flow from CD. So finally, you can see that for the 2-year AI, so the 150 millimeter diameter pipe is okay, right? It's suitable because we can see that for pipe DE, the peak flow is 13.4, less than the 21, So that means the 150 millimeter diameter, the pipe is okay. It's okay. So how about the major storm? The major storm event. So similarly, we can calculate the major storm event for 50 years. So you can see that it is here. So for these calculations, actually, you can see that for the pipe AB, for pipe BC, and pipe CD, so the peak flow less than the capacity, but for the pipe DE, okay, so you can see that the peak flow is larger than the capacity of the road. So that means what that means? That means the road. So the road should be capable to temporarily hold 1.77 liter per second of the water. If we want to use the 150 millimeter diameter diameter pipe. But of course, you can change. Of course, you can change the pipe size. Okay, for DE, for example, we can use normally increasing step 70 5 mm. So you can change to a 225 millimeter diameter the pipe. Okay, to try another large size, larger diameter pipe. Okay, change. Okay, so that means to make sure the peak flow less than the capacity of the pipe. Okay. So for the pipe size, okay, normally range from 150 millimeters up to 1,200 millimeters. Actually, normally increasing in steps of 75 millimeter. So above 1,200 millimeters, so the step size is 150 millimeter up to 2,500 millimeter. Okay. So that means these examples are how to calculate the peak flow for each pit, and also how to determine the pipe size in the drainage system. So any questions? No, I give another poll. Oh, seems to receive questions. Here's question. Oh, no question. Okay. Now I have another poll. I'm not sure whether you notice that minus roughness coefficient. Another pose. Okay, it is a true or false poll about the minus roughness coefficient. Is dimensionless or not dimensionless? I see only 9 students respond to the poll. How about other students? Okay. Okay, I waited 1 more minute. Now I'm uploading the exercise. Uploading the exercise. Okay, I'm not wait anymore. So actually, this question actually is a true or false question. Actually, is not the coefficient is not dimensionless. Actually, this coefficient, this minus roughness coefficient, has a unit and has a unit. Okay, next we are going to have some okay about the steps in design. So actually, this is a summary of the steps in the urban drainage system design. So actually, there's 5 steps. Okay, the first one is select the rainfall runoff model. Normally, we use the rational method. Okay, then select the return period. Okay, for example, minor event 2 years, major event 50 years, and step 3, prepare a preliminary layout. Okay, and the step 4, calculate the appropriate I for 2 years and 50 years storm. or you can get that from the curve or table, and then calculate the runoff to each pit, and also the PEPs. Now next we're going to have some kind of the tutorial questions actually about the rational method. Let me see. Now this is the workshop tutorial I upload to the Canvas. Have you downloaded that? Have you downloaded that? Okay, great. So now let's look at the question 2. Question 2. Move to question 2. Move to question 2. Okay. Now here's the question 2. Actually, question 2. Actually, this using the rational method. Okay, and also to find the peak discharge into each inlet. Okay, and also the discharge capacity and the required discharge capacity for each PEP segment. Use a 50-year return period. And also you can see we assume the slope is slope of the AB is 1%. Using the rational method, and also the friction factors given. Okay, and also this is the layout. This is layout of the catchment, of the subcatchment, layout of this drainage system. So you can see that for this questions, I can see there are 3 subcatchment: A1, A2, and A3, and also the area given, the C, the coefficient given. Okay, and the runoff coefficient given, and also the time also given. Okay, means the concentration time is also given. So so that means you don't need to calculate the concentration time. Okay, so you need to determine the flow to peak discharge to the inlet, to the pit A and to the pit inlet B, and also to size the PEP, and also find out the discharge capacity for each PEP segment. So very easily we need to use the rational method for these questions. Okay. Now I can show you the solutions for these questions. Okay. Now actually there are 3 subcatchment, A, and 2, and 3. And also you may notice that you can use the version you downloaded. Okay, for the question you can use the refer to the your downloaded version of questions. You can see that for the subcatchment 1 and the subcatchment 2, the flow to the inlet A, right, to the inlet A, and also for the subcatchment to the inlet B. Okay, you can find out to inlet B, and also the surface runoff coefficient given. Okay, the roughness coefficient given. So and the area given, the time of concentration given. So and also you can get the intensity. So you can get intensity from the table, or from the ADF curve, or from the ADF table. Okay. So by using the rational method, so you can get the Q, the peak flow to the inlet A, and also you can get the peak flow to the inlet B. Okay. So this is the inlet, means the peak discharge. By using the rational method, you can calculate the peak discharge to each inlet. Okay, to each inlet. Any problem? I think. Okay, no questions. Okay, clear. Okay, good. Now next we need to determine the PEP. The PEP. PEP, required discharge capacity for each PEP segment, Now for the PEP AB, so the equivalent impervious area is this one. For the PEP AB, means from subcatchment 1 and from the subcatchment 2. Okay, so here is the time concentration. So here is the intensity. So we can get the peak discharge to the PEP AB, actually it is 11. So it is the same with this the peak discharge to the inlet. Okay, same with the peak A, the peak discharge to the inlet A. Now for the PEP BC, for PEP BC, be careful. For PEP BC, actually there will be 3 subcatchment also flow to the PEP B. Okay, okay, the 3 subcatchment the flow to the PEP B, So that means the PEP BC, so need to deliver the runoff from all 3 catchment, all 3 subcatchment, right? So the time 31.5, because we need to calculate the time, the PEP time. Okay, the flow in the PEP AB, the time. Okay, then we find out the intensity. We found out the intensity from the from the IDF curve or table, so we can get the peak discharge in the to the PEP BC, Okay, now for the time concentration of the PEP BC, how can we get the time concentration? So that means we need to get the time, the PEP time, means the time of the flow in the PEP, So we'll use the Wishbacher, the Darcy-Wishbacher equation. This equation, actually we introduced that already. Okay, use this Darcy-Wishbacher equations, so we can get the time. So we can get the firstly we need to get the velocity in the PEP AB, velocity in the BC, because the L is given, the length of the PEP BC is given, the diameter is we assume the diameter is 150 millimeters. Okay, 150 millimeters, and also the F is given. The F is what? I can't remember. The F is what? The F is 0.02, right? Okay, the F is 0.02. Okay, so the HF over L. So HF over L is the what? Is the slope. Slope is 1%. I remember. Okay, so then you move the L to this side. Okay, you move the L to this side. Over L. So HF over L is actually the slope. Slope is 1%. 1%. F is 0.02. D is the 150 millimeter. The G is the 9.81. Okay, so very easily you can get the capacity here. You get capacity. Is capacity of the pipe, and also get the of course you can get the velocity. So you can get the velocity first. Okay, you get the velocity, and also you can get capacity of pipe and get the time. The pipe in the PEP. Okay, in the PEP. So that means the travel time. Okay, flow time. Flow time in the PEP. So 1.5. So 1.5 minutes. So around 1.5 minutes. Okay, 1.5 minutes. So that's why we can see that here is the so here is the how to get the concentration time. Okay, for the PEP BC. This is the calculations. This is calculation how to get the time of concentration. So that means we use the Darcy-Weisbach equations. So we move the L to the left side. So this is a slope. So we know the friction factor. We know the diameter. So we can get the velocity. So we can get the capacity. So with the velocity, so we can get the the time in the pipe AB, time in the pipe AB. Okay. Any questions? Any questions? Okay, good. Next, we have a look at another question. So question I see is question 3. Now question 3. Question 3. Sorry. Now, question 3, actually, there are two subcatchment, parkland and the paved area. Okay, and parkland, you can see that the flow into the pit A. Okay, flow into the pit A. Let me see the questions. And also the slope in the pit A is 2%, in the 2%. Okay, and also the of course the paved area to the pit B, to the pit B. Okay, so and also the N for the grass surface given and the runoff coefficient, given. Okay, and the rainfall intensity for 2 years. Okay, rainfall for 2 years. Okay, and I'll assume the slope is 1% and the friction factor is 0.015. Okay, so actually you can see that actually you need to determine the question is the flow into pit AB and the flow into BC. You need to calculate the flow in BC and calculate the flow in AB. Pit A and pit B. Okay. Now the difference of this question with the question 2 is that these questions you can see the concentration time is unknown, right? So in question 2, the time of concentration given, okay, for each subcatchment, but for this one, no given, so not given, so you need to calculate, okay, calculate. So let's look at how to calculate the time of concentration of the subcatchment. Now you can refer to the questions you downloaded from Canvas. Okay. First, we need to determine the time concentration of the catchment of the subcatchment A, parkland of the parkland. Okay, of the parkland. And also the time of the concentration of the paved area. I see is given. Okay, is given. The paved area, the times of concentration, is 6 minutes. 6 minutes, but the parkland, the time of concentration is unknown. Okay, so you need to calculate. Okay, so to calculate the parkland, so we normally use this. Let me see. Normally use this equations. Use this equation. So as I mentioned that you cannot get this one directly, you need to list a table. You need to prepare a table. So firstly, we prepare this table. T and I, and the T times I 0.4 power. Okay. So of course, this is the I is from the IDF table or IDF curve. Okay, for different time of concentration. Okay. Now this question you can calculate the LS. You can calculate the L and S. Calculate the L, the length, and the S is given. The S is 2%. Okay, the S is 2%. Okay, the N, the roughness of the surface is 0.0. It's also given. The roughness of N is given, right? N is also given. So you can get the you can get what? Now you can get this one. You can get this one. This one. I can get this one. Get this one. So because the L is no, the L is no, the N, the roughness is no, and also the S is no. Okay, so you can get this one. So there, actually, this one is what? Is this one? Is this value? This value. Okay, this value. So this one, after calculation of, you can get this one. Get this one. This is means that the time times I 0.4 power is 52.329. Okay, so you can get the time of concentration. How to get there? Find it out from table. Okay, so you can see that by using this one, you can see, oh, this is around what? It is around 52.4, right? Okay, so 52.4, you can find out the time is what? Time is 7. Time is 7. Okay. So that means the overland. So that means this question is for the parkland. For the parkland, you need to calculate the overland time, the overland flow time. Okay, 7 minutes. Any questions? Okay, yeah. So that means this this slide is showing how to get the overland time of concentration. Overland time of concentration. So then we can calculate the peak flow to the peak A. So peak A is the area times the runoff coefficient and times the concentration time, and also times the intensity from the IDF curve or table, and also we can get the peak flow to the peak A. And also for the paved area, so the time of concentration is given. Okay, it's given, so we can easily get the peak flow this one to the peak B. To the peak B. So next we need to determine the flow, the peak discharge to the pipe BC, the pipe BC. Now for pipe AB, so the peak discharge is also the same of the with pit A. Okay, with pit A. So how about the peak discharge to the peak flow to the in the pipe BC, in the pipe BC. So that means all these two subcatchment contribute to the pipe BC. But you need to determine the time of concentration. Okay. So you can see the time of concentration. So the longest time of concentration is 7 minutes. Okay, 7 minutes. But you need to calculate the time in the pipe, in the pipe AB. The time in the pipe AB. So similarly, so we use the Darcy-Weisbacher equation. We use Darcy-Weisbacher equation to find out the time in the pipe AB. So because the slope is 1%, the F is given. The F is friction factor is 0.0015. I remember. And also we also assume here is different. Here we assume the pipe size is this one, 225 millimeter. Okay, so you can get the velocity, get the maximum, get the capacity, So you can calculate the time in the pipe, around 1 minute. And also you need to check the capacity. Whether the capacity is larger than the peak flow. For example, now here you can see that the peak flow in the pipe AB is 41.4. Okay, so we can see that this is larger than, right? So this is larger than the peak flow. So this is suitable for pipe AB. Means the pipe AB, the diameter 225 millimeter is suitable. Now next after we get the time, so we can get the peak flow in the PEP BC. So you can see that the peak flow in PEP BC is 187. So the 225 millimeter diameter is not suitable. Okay, is not suitable. Okay, so that means for PEP BC, you need to use another larger PEP size. You need to use a larger PEP size. So I think you need to use maybe 500. 500. Okay. But this question, you can see that this question does not require to size the PEP, to size the PEP BC, to size the PEP. Okay. But if the question asks you to size the PEP BC, so you need to try another PEP size. For example, let me see, not 500. At a step at 75 millimeter means 300, 375, 450. Maybe we could try 450, 450, or 525 millimeter. Okay. So this is the question 3. Any questions? Okay, great. Let's make a summary. So I think the for the rational method actually, and the you need to be clear the contributions of the subcatchment. Okay, for each pit. So which subcatchment contribute to the pit, and also for the PEP size also. When you calculate the downstream, we calculate the downstream pit, downstream PEPs. You need to consider the you need to change the time of concentration, because the time concentration will include the PEP time, the flow time in the PEP, Okay. In the upstream, the flow time in upstream PEPs, And another point you need to be careful is about the overland time of concentration. Overland time of concentration. So, for example, this question, question 3, actually you can see the examples how to get the overland time of concentration, right? Okay, so that means by using this equation, you cannot get the this equation. You cannot get the time of concentration, means overland time of concentration directly. So you need to list a table. Okay, list table. For example, step 1, you need to list a table. List table. Okay, and step 2, with a given L, N, and S, you can calculate this one. Means this is the step 2. Now step 3, or back to this the table. Step 3. So after you get this value in step 2, you go back to this table to find out the time. So so this is, I think this is the you need to be careful when you determine the time of concentration for the overland. Okay, for the rational method, do you have still have any questions? Okay, great. Actually, this actually now next we are going to have an exercise so for your practice. Actually, this is from the 2017 exam, the question 1. Okay, actually you can download the exam from the Canvas. Actually, I already upload the exam paper. So today I think we do not have time to do this exercise. Okay, so I leave it tomorrow morning. Okay, so I think we today we introduce the urban drainage designs, and also especially we focus on the we talk about the rational method. Okay, and also the factors. Okay, the factors for the affecting the concentration, the time of concentration, and also the ARI, IDF curves. Okay, so means all these are used are important for the urban drainage system design. And also for the rational method, actually it's a simple method to use to estimate the peak flow. To estimate the peak flow of the catchment. Normally for the small catchment, normally used for the less than 25 square kilometers. Okay. And also we learn how to determine the times of concentration. Actually, there are 3 different types of time of concentration: overland, channel flow, and also in the pad. And also we also need to learn how to determine the size of the peak flow. Now we know how to calculate the peak flow in the pit and also in the pad, and also we know how to determine the size of the pads, Okay, if you have no more questions about the rational method, I would say we stop here today. Okay, so we will resume tomorrow morning. Okay, with the exercise about the rational method. Okay, so see you tomorrow morning.